Now in this lecture we'll answer two questions. The first question, we find out the size of this angle AMQ is equals to x. We have to find out the value of angle x. And in the second question, we find out the area of this circle that is inscribed by trapezoid ABCD. So we start with the first question. In the drawing, we have a semicircle. AB is the diameter of this semicircle. Point O is the center of this semicircle. Inside this semicircle, we have square PQSO. In addition, we know that OS equals to SB. And our task is to find out the size of angle AMQ that equals to x. We have to find out the value of angle x. So first of all, we know that all the angles in square PQSO are right angles. So here, this is a right angle. This is also a right angle. And this is a right angle. AB is the diameter of this semicircle, so AB is the diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line AB at this point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So according to rule 3, the sum of the angles on the upper side of the straight line AB at point S must be equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point S? We have this angle, that is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. According to rule 3, of course. In the next step, we join points B and Q together by a straight line. And we'll extend line segment BQ until it touches the circle. We'll define the touching point of the extended line segment BQ with this circle. This point is point N. By doing this construction, we can do the right triangle QBS. We know that all the sides of a square are equal to each other. That is to say, side OS is equal to side QS. OS equals to QS. So we can write here that OS equals to QS. And it is given as the question that side line segment OS equals to line segment SB. And from this equation, QS equals to OS equals to SB, we will derive that QS equals to SB. QS equals to SB. So QS equals to SB. Those two sides are equal to each other in triangle QSB. And we have the rule that in front of equal sides in the triangle there are equal angles. So if you relate to the right triangle QSB, in front of those two equal sides, we have those two angles that must be also equal to each other in their lengths. So if we define the size of this angle as y, Then the sides of this angle must be also equal to y, because those two angles are equal to each other because they are located in front of those two equal sides. We know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in the right small triangle QSB must be equal to 180 degrees. So which angles we have in the right triangle QSB? Y plus y is 2y plus 90 degrees. In total, the sum of those three angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So I repeat again, in the right triangle QSB, the sum of the angles must be equal to 180 degrees. So 2y plus 90 degrees equals to 180 degrees. Here we subtract 90 degrees from the equation, and we get that 2y equals to 180 degrees minus 90 degrees is 90 degrees. So 2y equals to 90 degrees. Here we divide this equation by 2, and finally we get that the missing angle y equals to 90 degrees over 2 is 45 degrees. So angle y equals to 45 degrees in its size. So actually, this is angle y is equals to 45 degrees in its side. And this is also angle y is equals to 45 degrees in its size. We joined points B and Q by straight line, and then we extended the straight line BQ by straight line. In this way we got the straight line BN. When you extend the straight line by straight line, the result is a straight line. So BN is also a straight line. So if you focus on the left side of the straight line BN at point Q, here the sum of the angles must be equal to 180 degrees. According to rule 3, that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angle we have at the left side of the straight line BN at point Q? We have 45 degrees plus 90 degrees. Plus this missing third angle, that is the angle NQP. So the sum of those three angles must be equal to 180 degrees according to rule 3. $90 degrees plus 45 degrees is 135 degrees, plus the missing angle NQP. Total, they must be equal to 180 degrees according to rule 3. So here we subtract 135 degrees from this equation, and we get that the missing angle NQP is equal to 180 degrees minus 135 degrees is 45 degrees. So actually, this is the missing angle NQP is equal to 45 degrees in its size. In the next step, we will join points M and N together by a straight line. we join points A and then together by straight line. By joining points A and N, we can get triangle A and B. This is triangle A and B. Triangle A and B subtend on AB the diameter of this semicircle. And according to rule 7, any triangle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its size. So I click on rule 7. According to rule 7, if a triangle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle. This is triangle ACB that subtends on AB, that is the diameter of this circle. And according to this rule 7, triangle ACB must be equal to 90 degrees in its size because it subtends on the diameter of the circle. So we can implement rule 7 in our drawing. Well, because in our drawing we have triangle A and B that subtend on AB, that is the diameter of this semicircle. And therefore, according to rule 7, triangle A and B must be equal to 90 degrees in its size. So triangle A and B equals to 90 degrees in its size according to rule 7. We continue to focus on this right triangle, triangle A and B. On the right triangle A and B, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle A and B, we know that in any triangle, in front of equal angles, we have equal sides. So in the right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. That is to say, side AN equals to side NB. AN equals to NB. And therefore, triangle A and B is an isosceles triangle. Triangle A and B is simultaneously an isosceles triangle and the right triangle. So right now, if we found out that triangle A and B is an isosceles triangle. So, in the isosceles triangle A and B, AB is the base of the isosceles triangle. Again, AB is the base of the isosceles triangle A and B. But AB is also the diameter of the semicircle. AB is also the diameter of the semicircle. So, here we can implement rule 24, on rule 24. According to rule 24, the perpendicular to the base of an isosceles triangle bisect the base. So, in the drawing we have the isosceles triangle ABC. Triangle ABC is an isosceles triangle because side AB equals to side AC. BC is the base of this isosceles triangle ABC. So, from point A, we draw perpendicular to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule, rule 24, the perpendicular AO to the base BC bisect the base BC. That is to say, it divides the base BC into two halves. Each half equals to BC over 2. So the first half BO equals to BC over 2, the second half OC also equals to BC over 2, and of course BO equals to BC. BO equals to OC. Those two halves are equal to each other. So we can actually implement rule 24 in our drawing. In our drawing, if we draw the perpendicular from point N to the base AB, then the perpendicular to the base AB bisects the base AB. AB is the diameter of this semicircle. So if the radius of this semicircle is R, then the diameter AB must be equal to 2R. So AB is the base of the isosceles triangle A and B, and it is also the diameter is equals to 2R. And according to rule 24, the perpendicular from point N to the base AB bisect the base AB. So each half must be equal to AB over 2. AB over 2 is 2R over 2 because AB equals to 2R. 2R over 2 is R. So the first half AO must be equal to R, that is the radius of the semicircle, and the second half OB must be also equal to R. And because of the fact that the perpendicular from point N bisects the base AB, it means that the perpendicular from point N must touch the base AB at its midpoint. So the perpendicular from point N must touch the diameter AB at its midpoint. And we know that the midpoint of any diameter is the center of the circle or the center of the semicircle. So the perpendicular from point N must touch the diameter AB at its midpoint. And the midpoint of the diameter AB is at the center of the semicircle, that is point O. According to what is given in the question, O is the center of the semicircle. So the perpendicular from point N to the diameter AB will touch the diameter AB at point O, that is the center of this semicircle. Okay, so we draw the perpendicular from point N to the base AB, and because of the fact that the base AB has been bisected into two halves, each half equals to R, that is the radius of the circle, the midpoint of the diameter AB is the center of the semicircle, that is point O. So the first half AO is the radius of this circle, of this semicircle. The second half OB is also the radius of the semicircle, that is R. And the perpendicular from point N will touch the diameter AB at point O, that is the midpoint of the diameter AB. Because of the fact that the midpoint of any diameter is at the center of the semicircle or a circle, and O is the center of this semicircle. So NO is perpendicular to the diameter AB, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We know that the opposite sides of a square are parallel to each other. So in square PQSO, side PQ is parallel to the opposite side OS. Those two angles are defined as corresponding angles, and they are located between the parallels PQ and OS, and therefore they must be equal to each other in their sizes. But this angle equals to 90 degrees, and therefore this angle must be also equal to 90 degrees inside, according to the rule that corresponding angles between parallel lines are equal to each other. And again, we have the rule that says that corresponding angles between parallel lines are equal to each other. In the drawing, we have line 1 that is parallel to line 2. Line 3 cuts the two parallel lines at those 2 points. Those two angles 1 and 2 are defined as corresponding angles and are located between the parallel lines line 1 and line 2. And therefore, they are equal to each other in their sizes. That is to say, angle 1 equals to angle 2. So we implemented this rule in our drawing. In our drawing, PQ is parallel to OS, and those two angles are defined as corresponding angles, and they are located between the parallel lines PQ and OS, and therefore they are equal to each other in their sizes. But this is a right angle according to our construction, therefore this angle must be also equal to 90 degrees in its size. Okay. So in the drawing we have triangle ABN. This is triangle ABN that subtend on AN. Again, triangle ABN is equal to 45 degrees in size and is subtend on chord NA or AN. Likewise, we have another triangle that is angle AMN. Angle AMN is a triangle. This is angle AMN that subtend on the same chord called AN, exactly like this triangle ABN. So those two triangles subtend on the same chord called AN, and therefore they must be equal to each other in their sizes, according to rule 16. Again, according to rule 16, triangles that subtend on the same chord are equal to each other. In the drawing, we have a circle. Inside this circle, we have chord AB. Those two triangles, they are both subtend on chord AB, and therefore they are equal to each other in their sizes. That is to say, triangle AOB equals to triangle ACB, because they subtend on the same chord called AB, or alpha equals to beta. So, triangles that subtend on the same chord are equal to each other. We can implement rule 16 in our drawing, because in our drawing, this is triangle ABN that subtend on chord AN. This is triangle AMN that also subtend on the same chord called AN. And therefore, according to rule 16, those two triangles that subtend on the same chord called AN must be equal to each other in their sizes. But this is triangle ABN that is equal to 45 degrees in size. Therefore, this triangle AMN, which is also subtend on the same chord called AN, must be also equal to 45 degrees in size, according to rule 16. This is triangle AMN. It must be also equal to 45 degrees in size, because it's subtend on the same chord called AN, exactly like triangle ABN. And triangle ABN equals to 45 degrees, and therefore triangle AMN must be also equal to 45 degrees in size, according to rule 16. In the next step, I will prove that quadrilateral PNMQ, this is quadrilateral PNMQ, that quadrilateral PNMQ is a cyclic quadrilateral. And again, we'll prove that quadrilateral PNMQ is a cyclic quadrilateral. That is to say, quadrilateral PNMQ can be blocked by a circle. Okay? Or that quadrilateral PMNQ can be inscribed by a circle. So, first of all, this is angle NQP. This is again NQP, is equal to 45 degrees inside. Angle NQP is also triangle NQP. So actually copied this triangle NQP. This is also angle NQP. This is equal to 45 degrees in size to an upwidge. So this is angle NQP. This is also triangle NQP. And we have the rule that all the triangles can be inscribed by a circle, or all the triangles are cyclic. That is to say, we can block this triangle NQP by a circle. So I block this triangle NQP by this circle. And this is angle NQP, is equal to 45 degrees in its size. So in the next step, we will keep the size angle NQP, it is equal to 45 degrees in its size, and we will rotate this angle NQP around this circle without changing the size of this angle. So NP will be the axis of triangle NQP, that it will not move, and we will just move the vertex Q along this circle without changing the size of this angle NQP. This is 45 degrees. So remove angle NQP along this circle, around this circle, without changing the size of angle NQP. In this way we create infinite angles that each of them will be equal to 45 degrees in size, because we will not change the size of angle NQP. So one out of those infinite angles will be angle NMP. This is also equal to 45 degrees in its size. This is angle NMP. This is angle NMP. This is equal to 45 degrees in its size. Okay. So by moving angle NQP around this circle without changing the size of angle NQP, that is 45 degrees, we created angle NMP. This is angle NMP. This is also equal to 45 degrees in its size. In the next step, we will join points M and Q together by a straight line. By doing this construction, we created a quadrilateral NMQP. This is quadrilateral NMQP. That is definitely inscribed by this circle. Okay, this is quadrilateral NMQP. That is inscribed by this circle. So in this way, we prove that quadrilateral NMQP is a cyclic quadrilateral, because we block this quadrilateral NMQP by this circle. So in conclusion, I know that quadrilateral NMQP is the same quadrilateral NMQP, like in the original drawing, is a cyclic quadrilateral, because we blocked quadrilateral NMQP by this circle. So we can actually found out that quadrilateral MNQP is a cyclic quadrilateral. So I will draw a circle around this quadrilateral NMQP, because it is a cyclic quadrilateral. So the red circle blocks this quadrilateral NMQP. Why the red circle blocks this quadrilateral? Because all the four vertices N, M, Q, and P are located on the red circle. Therefore, quadrilateral NMQP is inscribed by this red circle. And we have the rule that says that the sum of the opposite angles of a cyclic quadrilateral is equal to 180 degrees. Repeat again, the sum of the opposite angles of a cyclic quadrilateral is equal to 180 degrees. Repeat again on the rule. According to the rule, the sum of the two opposite angles in a cyclic quadrilateral is equal to 180 degrees. So quadrilateral NMQP is a cyclic quadrilateral, and therefore the sum of those two opposite angles in quadrilateral NMQP must be equal to 180 degrees. So this is angle NPQ, that is the right angle, plus the size of this opposite angle, that is angle NMQ. In total, the sum of those two angles must be equal to 180 degrees. So the sum of those two opposite angles must be equal to 180 degrees according to the rule that I presented to you. This is angle NQP, this is the right angle, plus this is angle NMQ, angle NMQ total equals to 45 degrees plus x. Again, angle NMQ equals to 45 degrees plus x. In total, the sum of those two opposite angles in quadrilateral NMQP must be equal to 180 degrees. $90 degrees plus 45 degrees is 135 degrees, plus x in total must be equal to 180 degrees. Here we subtract 125 degrees from this equation, and we get that the missing angle x, that is the angle that we are looking for in this question, is equal to 180 degrees minus 135 degrees is 45 degrees. So this is the missing angle x, that is also equals to angle AMQ. So angle AMQ is equals to x is equal to 45 degrees in its size. And that is the answer to the first question. I repeat again, if you found out that angle AMQ is also defined as angle x, this angle equals to 45 degrees in its size. So we finish with the first question. In the next step, I will present to you the second question, and for the second question of this lecture. In the second question, our task is to find out the area of this circle that is inscribed by trapezoid ABCD. Again, this circle is inscribed by trapezoid ABCD, or trapezoid ABCD blocks this circle. And our task is to find out the area of this circle that is inscribed by this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This trapezoid ABCD, side BC is parallel to the opposite side AB, and therefore quadrilateral ABCD is the trapezoid because it has one pair of parallel sides. Side DC is parallel to the opposite side AB. Again, a trapezoid is a quadrilateral with one pair of parallel sides. In quadrilateral ABCD, side DC is parallel to the opposite side AB, and therefore quadrilateral ABCD is a trapezoid. The two parallel sides, that is to say DC and AB, are defined as the bases of the trapezoid ABCD. So if we define the base DC as A, that is to say the base DC equals to A written in itself according to our definition, and the base AB is B, then the area of this trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say A plus B, times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. So again, if we found out that a trapezoid is a quadrilateral with one pair of parallel sides, and the area of any trapezoid equals to the sum of its two parallel bases. In this case, it is A plus B times the height edge over 2. So, first of all, we define the relevant points to this question with letters. We define the point of tendency of tangent DC with this angle. This point is point E. Likewise, we define the point of tendency of tangent DA with this angle. This point is point F. And finally, we define the point of tendency of tangent AB with this angle. This point is point G. We define the center of this angle. This point is point O. And we define the radius of this circle as X. The radius of this circle equals to X according to our definition. In the next step, we'll join points O and G together by a straight line. Point O is the center of this circle, point G is the point of the circle itself, therefore OG is the radius of this circle is equals to X. So here we can implement rule 1. Repeat quickly on rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle. This is tangent AB, that is tangent to this circle is point M. In addition, we have the radius OM that is equals to R. The radius OM that is equals to R is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So can we implement rule 1 in our drawing? We have the radius OQ that is equals to X. The radius OQ is drawn to point Q, that is the point of tendency of tangent AB with this circle. And whenever you have radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius QO. If AB is perpendicular to QO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. In the next step, we will join points O and F together by a straight line. OF is of course the radius of this circle, is equals to X, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. In the next step, we join points O and E together by a straight line. O is, of course, the radius of this circle is equal to X. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So by doing this construction, we can do quadrangle DEOF. In quadrangle DEOF, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this 4 rectangle. In total, they must be equal to 360 degrees. According to the rule, then the sum of the angles in any quadrangle is equal to 360 degrees. And therefore, this 4 rectangle must be equal to 90 degrees in its size. So, in the upper quadrangle DEOF, we have 4 rectangles. According to rule 5, any quadrangle that has 4 rectangles must be at least a rectangle if not a square. So, related to quadrangle DEOF, it's a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So, in rectangle DEOF, side EO must be equal to the opposite side DF. But EO is x, therefore the opposite side DF must be also equal to x units in its length. Likewise, in the lower quadrangle OFAG, we have 1, 2, 3 rectangles. And therefore this 4th rectangle must be equal to 90 degrees in its size. So can relate to quadrangle OFAG is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OFAG, side OG must be equal to the opposite side FA. But OG is x, therefore the opposite side AF must be equal to x units in its length. So in total, we can remember that the length of DA is x plus x, that is 2x. So DA equals to 2x units in its length. DA is absolutely a straight line because DA is one side of trapezoid ABCD, therefore it must be a straight line. So DA in total equals to 2x units in its length. In the next step, we define the length of side DC as A. We know that side AB equals to 3 units in its length, according to what is given in the question. AB equals to 3. In the previous lecture, we already proved that in trapezoid ABCD, side DA plus the opposite side CB equals to side DC plus the opposite side AB. Again, we already proved that DA plus CB equals to DC plus AB according to rule 2. So we use this thing in our question without any repetition of the proof. So we only found out that DA plus CB is equal to DC plus AB. And again, in the previous lecture, we already proved that DA in trapezoid ABCD side DA plus the opposite side CB equals to side DC plus the opposite side AB according to rule 2. DA equals to A. No, DA. No. This is side DA. This equals to 2x. Plus CB. CB is the missing side of Liberty Cities. This is side CB. And it is equals to DC. DC is A, according to the definition, plus AB. AB equals to 3 units in its length, according to what is given as the question. AB equals to 3. So in total we found out that 2x plus cb equals to a plus 3. Here we subtract 2x from this equation, and you get that the missing side cb is equals to a plus 3 minus 2x. So actually, this is the missing side cb of trapezoid ABCD, and it is equals to a plus 3 minus 2x units in its length. So write it down. Side cb, the missing side cb, equals to a plus 3 minus 2x units in its length. In the next step, we will do a construction. This is to say, from this point C, we will go perpendicular on AB. Again, from point C, we will go perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point M. By doing this construction, we created the big quadrilateral DCMA. Inside the big quadrilateral DCMA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must equal to 90 degrees in its size. So in quadrilateral DCMA we have 4 angles, and therefore we can relate to quadrilateral DCMA is a rectangle. Slightly long. The big quadrilateral DCAM is a rectangle because it has 4 right angles. But you also know that the opposite sides of a rectangle are equal to each other. So an rectangle DCAM, side DC must be equal to the opposite side CM. But DA is 2x, therefore the opposite side CM must be also equal to 2x units in its length. Likewise, according to the sum rule, the sum of rectangle DCMA, side DC must be equal to the opposite side AM. But DC is A, therefore the opposite side AM must be also equal to A units in its length. So AM equals to A units in its length. What is the length of the missing line segment MB? MB equals to AB minus AM. Again, AB minus AM equals to MB. So the number we found out that the missing line segment MB is equal to AB minus AM. So MB in total equals to AB is 3. Minus AM. AM is A. So in total we found out that the missing line segment MB is equal to 3 minus A units in its length. In the next step, I'll copy the big right triangle CMB in a new page, and we implement the Pythagoras theorem on this big right triangle CMB. This is the big right triangle CMB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. the hypotenuse CB equals to A minus 3 A plus 3 minus 2x units in its length. Side CM equals to 2x units in its length. And side MB equals to 3 minus 3 units in its length. So actually, this is the right angle CMB, the coefficient on the horizontal drawing. This right angle CMB, according to the Pythagoras theorem, CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. So written down, according to the Pythagoras theorem, in this right angle CMB, CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. CB is A plus 3 minus 2x, therefore CB squared is A plus 3 minus 2x squared, and is equals to CM squared. CM is 2x, therefore CM squared is 2x squared, that is 4x squared. Plus BM squared. BM is 3 minus 8, therefore BM squared is 3 minus 8 squared. Here we will open the brackets on both sides of this equation. According to the algebraic identity, it says that A minus B squared equals to A squared plus B squared minus 2 times A times B. Therefore, A plus 3 minus 2x squared equals to A plus 3 squared plus 2x squared, that is 4x squared, minus 2 times A plus 3 times 2x. And it is equals to 4x squared plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared minus 2 times 3 times A, that is minus 6A. We'll open the brackets of this expression A plus 3 squared. A plus 3 squared equals to A squared plus 3 squared, that is 9, plus 2 times A times 3, that is 6A. And also here plus 4x squared minus 2 times 2x is minus 4x. So total this expression equals to minus 4x times A plus 3. This equals to 4x squared plus 9 plus A squared minus 6A. So here we have A squared on both sides of this equation, so A squared gets cancelled. We have 9 on both sides of this equation, so 9 also gets cancelled. And we have 4x squared on both sides of this equation, so 4x squared also gets cancelled. So after cancel all those expressions, this side of the equation we left only with 6A minus 4x times A plus 3, and the other side of the equation we left only with minus 6A. So here we will add 6A for this equation, and also we will add 4x times A plus 3 simultaneously, and we get that 6A plus 6A is 12A equals to 4x times A plus 3. So here we divide this equation by 4, and we get that 12a over 4 is 3a, so 3a equals to 4x over 4 is x, so in total this expression equals to x times a plus 3. So 3a equals to x times a plus 3. Here we divide this equation by a plus 3, and finally we get that x that is the radius of the circle, is equal to 3a over a plus 3. And again, if we found out that x equals to 3a over a plus 3. In the next step, we calculate the area of this trapezoid ABCD according to the formula that I presented to you in the beginning of the lecture. The area of this trapezoid ABCD will be equal to the sum of its two parallel bases. This is to say it is DC plus AB times the height over 2. The height is cm because it's case 90 degrees with the two parallel bases, so it is the height cm over 2. So in total, if you found out that the area of this trapezoid ABCD equals to the sum of its two parallel bases, that is actually DC plus AB, times the height cm over 2. DC is A, plus AB. AB equals to 3 units in this life, according to what is given as the question, times the height CM. CM is 2x divided by 2. So in total, if you know that the area of this trapezoid ABCD, in total equals to a plus 3 times 2x over 2. We have 2 in the numerator and 2 in the denominator, so 2 get cancelled. So in total, if you know that the area of trapezoid ABCD is equal to a plus 3 times x units in its length. A plus 3 times x square units in its length. And again, if we found out that the area of trapezoid ABCD equals to a plus 3 times x square units in its size. But it is given the question that the area of this trapezoid ABCD is equal to 3 square units. So we can substitute the area of trapezoid ABCD by 3. So 3 equals to a plus 3 times x. So here we substitute x by 3a over a plus 3. And we get that 3 equals to a plus 3 times x. And x is 3a over a plus 3. So we have a plus 3 in the numerator and a plus 3 in the denominator, so a plus 3 will get cancelled. And we're left only with 3 equals to 3a. 3 equals to 3a. So here we divide this equation by 3 and finally get that a equals to 3 over 3 is 1. So a equals to 1 unit in its length. A equals to 1, and we already found out that x equals to 3a over a plus 3. And again, we have already found out that x equals to 3a over a plus 3. Now we can substitute a in this equation by 1 because a equals to 1. And we get that x equals to 3a. A is 1, so 3a is 3 times 1, that is 3, over a plus 3. A is 1, so a plus 3 is 1 plus 3, that is 4. So in total, if you found out that the radius of the circle equals to 3/4 units in its length. The radius of this circle x equals to 3/4 units in its length. Our task is to find out the area of this circle. So I'm sure you know that the area of any circle is equal to pi times the radius of the circle squared. And again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared, because x is the radius. So in total the area of our circle must be equal to pi x squared. So it is pi times x squared. X is 3/4, therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared, that is 16. So in total, if you all know that the area of this circle, that is the area that we are looking for in this question, is equal to either 9 pi over 16 square units in size in terms of numbers. The area of this circle equals to 1.767 square units in size. Okay, again, if you follow that the area that we are looking for in this question, that is the area of this circle, is equals to either 9 pi over 16 square units in size, or in terms of numbers, the area of this circle equals to 1.767 square units in size. So we finish with the second question. The next step, also as a lecture, we start with the first question, of course. In the first question, our task was to find out the size of this angle x, that is actually angle AMQ. This is angle AMQ. So we have to find out the value of this angle x. So in the drawing we have a semicircle. AB is the diameter of the semicircle, point O is the center of this semicircle. We know that OH equals to SO. Inside this semicircle we have square PQSO. Again, our task is to find out the size of this angle AMQ, that is equals to x. We have to find out the value of x. So first of all, we know that all the angles inside the square are right angles. So those 4 angles are all right angles. In addition, we know that all the sides of the square are equal to each other. That is to say, side QS equals to side SO. QS equals to SO. But it is given as a question that OS equals to SB. So from this equation, QS equals to OS equals to SB, we will derive that QS equals to SB. QS equals to SB. We know that AB is the diameter of this semicircle, so AB is the diameter, it is absolutely a straight line. So if you focus on the upper side of the third line AB at point S, here the sum of the angles must be equal to 180 degrees according to all three. All three said that the sum of the angles from one side of the third line is equal to 180 degrees. So in this case, the sum of the angles of the upper side of the third line AB at point S must be equal to 180 degrees according to all three. So which angles we have at the upper side of the third line AB at point S? We have this angle that is the right angle, plus this missing angle, so then the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points B and Q together by third line, and we extended the third line BQ by third line until it touches the circle. When you find the touching point of the extended line BQ with this circle, this point is point N. We have in the right triangle QSB, this is the right small triangle QSB. In front of those two equal sides, we have those two angles that must be also equal to each other and their sizes, according to the rule that in front of equal sides in the triangle are equal angles. So in front of those two sides in the right triangle QSB, we have those two angles that must be also equal to each other and their sizes. So if you find the size of this angle is y, then the size of this angle must be also equal to y, because they are equal to each other according to the rule that I mentioned. So in the right triangle QSB, the sum of the angles must be equal to 180 degrees. So which angles we have in the right triangle QSB? We have this angle that is y, plus this angle that is also y, plus this angle that is 90 degrees. In total, it must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right small triangle QSB, 2y plus 90 degrees equals to 180 degrees. Here we subtracted 90 degrees from this equation and found out that 2y equals to 180 degrees plus 90 degrees is 90 degrees. So 2y equals to 90 degrees. Here we divided this equation by 2 and finally found out that the missing angle y equals to 90 degrees over 2 is 45 degrees. So okay, this is the missing angle y that is equals to 45 degrees inside, and this is also the missing angle y that is equals to 45 degrees in its size. We have the joint points B and Q together by third line, and then we extended the third line by third line, and the result is Bn. When we extend the third line by third line, the result must be a third line. So Bn is a third line, and according to rule 3, if you focus on the left side of the third line and B at point Q, the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have on the left side of NB at point Q? We have this angle that is 45 degrees, plus this angle that is the right angle, plus this missing angle. In total, the must be equal to 180 degrees according to rule 3. So the sum of the angles of the left side of the third line BN is point Q must be equal to 180 degrees. That is to say, 45 degrees plus 90 degrees plus the missing angle NQP must be equal in total to 180 degrees according to rule 3. 45 degrees plus 90 degrees is 135 degrees. So 135 degrees plus the missing angle NQP in total must be equal to 180 degrees. Here we subtracted 135 degrees from this equation and finally found out that the missing angle NQP equals to 180 degrees minus 135 degrees is 45 degrees. So okay, this is the missing angle NQP that is equals to 45 degrees in its size. In the next step, we join points M and N together by third line, and also join points N and A together by third line. By joining points N and A, you can then triangle A and B. This is triangle A and B. Triangle A and B. Triangle A and B subtend on A and B. That is the diameter of this semicircle. And according to rule 7, any triangle that subtend on the diameter of the circle or semicircle, like this triangle A and B, must be equal to 90 degrees in its size. Therefore, triangle A and B that subtend on AB that is the diameter of the semicircle must be equal to 90 degrees in its size. So in the big right triangle A and B, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this furthest angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So, in the big right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths, according to the rule that in front of equal angles in the triangle, they are equal sides. So in the right triangle A and B, side AN equals to side NB. Side AN equals to side NB, therefore triangle A and B is an associated triangle. Triangle A and B is an associated triangle. And here we can implement rule 24. According to rule 24, first of all, AB is the base of the associated triangle, triangle A and B. So according to rule 24, the perpendicular to the base of an associated triangle bisect the base. So the perpendicular to the base from point N to the base AB bisect the base AB. So first of all, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to rule 24, the perpendicular from point N bisects the base AB. AB is also the diameter of the semicircle. So if the radius of this semicircle is R, then the diameter must be equal to 2R. So the diameter AB is equals to 2R has been bisected by the perpendicular from point N. Therefore, each half must be equal to AB over 2. Because of the fact that AB has been bisected, each half must be equal to AB over 2. AB is 2R, so AB over 2 is 2R over 2. So each half of the base AB must be equal to R. The first half is R, the second half of B is also R. And because of the fact that the diameter AB has been bisected into two halves, the perpendicular from point N will touch the diameter AB at its midpoint. And we know that the midpoint of any diameter is located in the center of the circle or a semicircle. So the midpoint of the diameter AB must be located at point O, that is the center of the semicircle. Okay? So the first half AO equals to R, and the second half OB also equals to R. And those two angles are both equal to 90 degrees according to our construction. Because we do the perpendicular from point N, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We know that the opposite sides of a square are equal. The opposite sides of a square are parallel to each other. So in square PQSO, side PQ is parallel to the opposite side OS. Those two angles are defined as corresponding angles, and they are located between the parallel lines OS and PQ, and therefore they are equal to each other. Those two angles are equal to each other according to the rule that corresponding angles between parallel lines are equal to each other. But this angle equals to 90 degrees, and therefore this angle must be also equal to 90 degrees according to the rule that corresponding angles between parallel lines are equal to each other. In the next step, I prove that quadrilateral NMQP, this quadrilateral is a cyclic quadrilateral. That is to say, we can block this quadrilateral NMQP by a circle. What is the meaning of the sentence to block a quadrilateral by a circle? It means that all the four vertices of this quadrilateral NMQP, that are N, M, Q, and P, must be located on the circle that blocks this quadrilateral NMQP. So why quadrilateral NMQP is a cyclic quadrilateral? Why you can block this quadrilateral NMQP by a circle? First of all, we have here angle NQP this is angle NQP that is equals to 45 degrees in size. Angle NQP is also triangle NQP. So I copy triangle NQP from the original drawing. This drawing. So this is triangle NQP that is equals from the original drawing. And this is again NQP that is equals to 455 degrees in size. We have the rule that all the triangles can be blocked by a circle. Therefore, triangle NQP can be blocked by this circle. So, I draw the circle around triangle NQP. And then, this is again NQP, that is equals to 45 degrees in size. We left side NP as a fixed side, it doesn't move, is the axis of angle NQP. Then we rotate angle NQP around this circle without changing the size of this circle, and without changing the size of this angle NQP is also 45 degrees in its size. So we rotated angle NQP that is equals to 45 degrees in its size around this circle. So in this way we create infinite angles that each of them will be equal to 45 degrees in its size. One of those angles will be angle NMP, that's subset on code NP, and it equals to 45 degrees in size. Because in the original drawing we have those two angles, that is to say angle NMP and angle NQP, they are both subset on the base NP, and they are both equal to 45 degrees in their sizes. So when we rotate angle NQP that is equal to 45 degrees in size without changing the size of this angle, we get infinite angles that each of them equals to 45 degrees in its size because we will not change the size of the angles. One of those two infinite angles will be angle NMP, that's subset on code NP, and it is equals to 45 degrees in its size. So in this way we get angle NMP that equals to 45 degrees in size. Then we join points M and Q together by straight line. By doing those constructions, we get the quadrangle NMQP. Therefore, we can say that quadrangle NMQP is definitely is a cyclic quadrangle. That is to say, it is inscribed by this circle. And therefore, in conclusion, we can write down that quadrangle NMQP is a cyclic quadrangle, that is to say, it can be blocked by a circle. Quadrangle NMQP is blocked by this circle. So you can write down that quadrangle NMQP is a cyclic quadrangle. Quadrangle NMQP is a cyclic quadrangle. Therefore, you can block this quadrangle NMQP by a circle. So I block this quadrangle NMQP by this red circle. The meaning of blocking a quadrangle by a circle means that all the four vertices of quadrangle NMQP, that is to say, for the vertex N, the vertex M, and the vertex Q and the vertex P, will be on the red circle. Okay, so you can see from the drawing that quadrangle NMQP is indeed blocked by this circle, or inscribed by this circle, red circle. And we have the rule that says that the sum of the opposite angles of a cyclic quadrangle must be equal to 180 degrees. So in quadrangle NMQP, that is a cyclic quadrangle, the sum of those two opposite angles must be equal to 180 degrees. So this is angle NPQ, that is the right angle, plus this angle that is actually angle NMQ, In total, the sum of those two opposite angles must be equal to 180 degrees according to the rule that I mentioned. Repeat again. The opposite sides of the cyclic quadrilateral NMQP must be equal to 180. The sum of the two opposite sides must be equal to 180 degrees. So angle NPQ plus the opposite angle PMQ must be equal to 180 degrees. Angle NPQ, this is angle NPQ, this is the right angle, plus this angle NMP, this is in total equals to 45 degrees plus x. In total, the sum of those two opposite angles must be equal to 180 degrees. Okay, again, angle NPQ is the right angle, plus angle NMQ is equals to 45 degrees plus x. In total, it must be equal to 180 degrees. 90 degrees plus 45 degrees is 125 degrees. So 125 degrees plus x, that is the angle that we are looking for in this question. Total, it must be equal to 180 degrees. So here we subtract 125 degrees from this equation and find out that the missing angle x equals to 45 degrees in its size. So this is angle AMQ, that is equals to x, is equals to 45 degrees in its size. So finish with the first question. The next step, I presented to you the second question and solve the second question of this lecture. In the second question, our task is to find out the area of this circle that is described by trapezoid ABCD. So, what is the definition of a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. In trapezoid ABCD, side DC is parallel to the opposite side AB. And the area of any trapezoid equals to the sum of its two parallel bases, that is to say it is DC plus AB, plus the height over 2. And again, quadrilateral DCBA is a trapezoid because side DC is parallel to the opposite side AB. The two parallel sides DC and AB are defined as the bases of the trapezoid ABCD. So if we define the length of DC as A and the length of AB, the base AB is B, then the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is to say A plus B times the height H over 2. The height H must create an integral with the two parallel bases. So a trapezoid is a quadrilateral with one pair of parallel sides, and the area of a trapezoid equals to the sum of its two parallel bases times the height over 2. So, in the drawing we have trapezoid ABCD that blocks this circle, and this circle is described by trapezoid ABCD. In addition, note that those two angles are both right angles. Side AB equals to 3 units in its length, and the area of this trapezoid ABCD equals to 3 square units in its size. Again, our task is to find out the area of this circle that is described by trapezoid ABCD. So first of all, we define the relevant points of this question with letters. We define the point of tendency of tangent DC with this circle, this point as point E. Likewise, we define the point of tendency of tangent DA with this circle, this point as point F. And finally, we define the point of tendency of tangent AB with this circle, this point as point G. In the previous lecture, we already proved that DA plus the opposite side CB equals to DC plus AB. So we use that fact in our question without proving it. But before that, we defined the center of this circle, this point as point O. We also defined the radius of this circle as x. And we join points O and E together. Join points O and G together by a straight line. Point O is the center of this circle. Point G is the point of the circle itself. Therefore, OG is the radius of this circle that is equals to x. The radius OG is equals to x. The radius OG is 1 to point G. That is the point of tendency of tangent AB with this circle. And whenever your radius is 1 to the point of tendency, then tangent AB will be perpendicular to the radius GO. If AB is perpendicular to GO, it means that this angle equals to 90 degrees. This angle also equals to 90 degrees according to rule 1. Likewise, we join points O and F together by a straight line. OF is the radius of this circle equals to x. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and G together by a straight line. O is the radius of this circle that is equals to x, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the upper quadrangle D, E, O, F, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing again, in total they must be equal to 360 degrees according to the rule. The sum of the angles in any quadrangle is equal to 360 degrees, and therefore this fourth missing again must be equal to 90 degrees in its size. So in quadrangle E, D, F, O, we have 4 angles. Therefore, we can relate to the small quadrangle EDFO as right angle because it has 4 right angles. But we also know that the opposite sides of right angle are equal to each other. So in right angle EDFO, side EO must be equal to the opposite side DF. But EO is x, therefore the opposite side DF must be also equal to x units in itself. Likewise, in the lower quadrangle OFAD, we have 1, 2 right angles. And therefore, this fourth angle must be equal to 90 degrees in its size. So in quadrangle OFAG, we have 4 angles, and therefore we can relate to this lower quadrangle OFAG as a right angle because it has 4 angles. But we also know that the opposite sides of right angle are equal to each other. So in OFAG, side OG must be equal to the opposite side FA. But OG is x, therefore the opposite side FA must be also equal to x unit in itself. So in total DA equals to x plus x, that is 2x. DA equals to 2x units in itself. DA is definitely a straight line because it is one side of trapezoid ABCD. So DA in total equals to 2x. We define the length of DC as A, that is to say, side DC equals to A units in itself according to our definition. AB equals to 3 according to what is given in the question. CB is the missing side. We have already proved that DA plus CB equals to DC plus AB according to rule 2. And again, we already proved in the previous lecture that DA plus CB equals to DC plus AB according to rule 2. DA is 2x plus CB. CB is the missing side, so it is, and it is equals to DC. DC is A plus AB, that is 3. So in total, if you want the 2x plus CB equals to A plus 3. Here we subtract 2x from the equation, and we found out that the missing side CB equals to A plus 3 minus 2x. This is the missing side CB, that is equals to A plus 3 minus 2x units in its length. In the next step, we did the construction, that is to say, from point C we drew perpendicular on AB. Again, from point C we drew perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point C and AB. This point is point M. By doing this construction, we get the quadrangle DCMA. In quadrangle DCMA, we have 1, 2, 3 right angles. The sum of 3 right angles is 470 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrangle DCMA we have 4 angles, and according to rule 5, any quadrangle that is 4 angles must be this right angle plus the square. So we relate to the big quadrangle DCMA, so right angle again because it has 4 right angles. But we also know that the opposite sides of the right angle are equal to each other. So in right angle DCMA, side DC must be equal to the opposite side AM. But DCZ, therefore the opposite side AM must be also equal to A units in its length. Likewise, according to the sum rule, in the sum of the DCMA, side DA must be equal to the opposite side CM. But DA is 2x, therefore the opposite side CM must be also equals to 2x units in its length. What is the length of the missing line segment MB? MB equals to AB minus AM. Again, AB minus AM equals to MB. So MB equals to AB minus AM. MB equals to AB, this is 3 according to what is going to the question. Minus AM. AM is A. So total MB equals to A minus 3 units in its 3 minus A units in its length. Because AB is 3. So MB total equals to 3 minus A units in its length. MB equals to 3 minus A units in its length. The next step, by copying the right triangle CMB in the new equation, we implemented the Pythagoras theorem, this right triangle CMB. According to the Pythagoras theorem, in any right triangle, the square of their products equals to the sum of the squares of the perpendiculars. So this is the right triangle CMB, that according to the original drawing. According to the Pythagoras theorem, in this right triangle CMB, CB squared, that is the square of their products, equals to CM square plus MB square. Again, CB square equals to CM square plus MB square. CB is A plus 3 minus 2x, therefore CB square is A plus 3 minus 2x square, and it equals to CM square. CM is 2x, therefore CM squared is 2x squared. 2x squared is 4x squared. And we have plus MB squared. MB is 3 minus A, therefore MB squared is 3 minus A squared. So in total we should find out that A plus 3 minus 2x squared equals to 4x squared plus 3 minus A squared. We open the brackets of both sides of this equation according to the algebraic identity that A minus B squared equals to A squared plus B squared minus 2 times A times B. According to the algebraic identity, we get that A plus 3 minus 2x squared equals to A plus 3 squared plus 2x squared minus 2 times A plus 3 times 2x. And it is equals to 4x squared plus 3 minus A squared. So it is 4x squared plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared minus 2 times 3 times 8, that is minus 6A. Open the brackets of this expression, A plus 3 squared equals to A squared plus 3 squared, that is 9, plus 2 times A times 3, that is 6A, and we have also 4x squared plus 4x squared, and it is equals to minus 2 times 2x is minus 4x, so in total this expression equals to minus 4x times A plus 3, and it is equals to 4x squared plus 9 plus A squared minus 6A. Here we have A squared on both sides of this equation, so A squared will get cancelled. We have 9 on both sides of this equation, so 9 also will get cancelled, and finally we have 4x squared on both sides of this equation, so 4x squared also will get cancelled. After we cancel all those expressions, in this side of the equation we have to only with 6A minus 4x times A plus 3, and the other side of the equation we have to only with 1 6A. So in the next step we added 6A and also 4x times A plus 3 to this equation simultaneously, and I have found out that 6A plus 6A is 12A equals to 4x times A plus 3. Here we divided this equation by 4 and finally found out that 12 over 4 is 3A and 4x over 4 is x, so in total this expression equals to x times A minus 3 times A plus 3. So in total we should find out that 3A equals to x times A plus 3. Here we divided this equation by A plus 3 and finally found out that x equals to 3A over A plus 3. In the next step we calculated the area of this trapezoid ABCD according to the formula that I presented to you at the beginning of the lecture. The area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is to say DC plus AB, times the height CM over 2. And again, the area of trapezoid ABCD equals to the sum of its two parallel bases, that is actually DC plus AB, times the height CM over 2. DC is A, plus AB is 3, according to what is given in the question, times the height CM, that is 2x, divided by 2. So in total, if you found out that the area of trapezoid ABCD equals to A plus 3 times 2x over 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we left only with a plus 3 times x. So in total, we should find out that the area of this trapezoid ABCD equals to a plus 3 times x. But it is given the question that the area of this trapezoid ABCD equals to 3 square units in its size. So we can substitute the area of trapezoid ABCD by 3. We did it, and we found out that 3 equals to a plus 3 times x. So we already found out that x equals to 3a over a plus 3. So we can substitute x by 3a over a plus 3. We did it, and we found out that 3 equals to a plus 3 times x, and 3 equals to a plus 3 times x, and x is 3a over a plus 3. We have a plus 3 in the numerator and a plus 3 in the denominator, so a plus 3 will get cancelled, and we left only with a 3 equals to 3a. Here we divided the equation by 3 and found out that a equals to 3 over 3, that is 1. So a equals to 1 unit in its length. A equals to 1 unit in its length, and we already found out that x equals to 3a over a plus 3. Now we can substitute a in this equation by 1, because a equals to 1. We did it, and we found out that a equals to 3a. A is 1, so 3a is 3 times 1, that is 3, over a plus 3. A is 1, so a plus 3 is 1 plus 3, that is 4. So in total, we found out that x, that is the radius of this circle, is equal to 3/4 units in its length. Our test is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared, and therefore the area of our circle, must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total, the area of our circle must be equal to pi x squared. So it is pi times x squared. X is 3/4, therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared, that is 16. So in total, we should find out that the area of this circle, that is the area that we are looking for in this question, is equal to either 9 pi over 16 square units in size, or in terms of numbers, the area of this circle equals to 1.767 square units in size. Okay, thank you very much.